Hello, everyone. It's my great honor to have the opportunity to present my work. My topic today is green and environmental materials for CO2 enhanced oil recovery and geological storage. First, I will give a brief introduction of the technical background. The global CO2 emissions are gradually increasing in recent years. In 2021, the global CO2 emissions were about 34 billion tons. The excessive CO2 emission caused the global warming in recent years, which results in many natural catastrophes. China has pledged that its emission will peak around 2013, reaching carbon neutrality by 2060. That means China's net carbon emission will reach zero by then. Carbon sequestration meets the national strategic needs of climate governance in China and provides technical support and system solutions to achieve greenhouse gas reduction target. The left figures present the number of global carbon capture projects in the operation and on the construction. The CCUS, UR, and the EGR means due to enhanced oil and gas recovery while achieving the CO2 sequestration in oil and gas reservoir geological body. CCS means CO2 capture and storage. The number of global carbon capture projects in operation and under construction is increasing in the near 10 years. As a result, the annual carbon capture capacity of global major projects is also increasing sharply during 2010 and 2023. Comparatively, the CCUS and EGR is the most practical carbon sequestration technique with annual carbon storage capacity of 33 megatons, accounting for around 94% of the total amount of global carbon reduction program. The heavy CO2 emissions have resulted in many natural catastrophes such as drought. Development of CCUS UR technology is a realistic demand of ecological protection to efficiently alleviate the contradiction between energy development and water resources shortage. Establishing integration technical model of CO2 UR and geological storage is critical for developing a conventional reservoir in China. 2. The challenges. To well-perform CCUS projects in the oil field, we still have some challenges to overcome. First, the viscosity of crude oil in the oil field of China is usually extremely high. Such high viscous oil is immiscible with CO2 as the reservoir conditions. Secondly, the oil reservoir is high heterogeneous and CO2 readily flows along the hypermain channels, resulting in the low CO2 sweep volume in the reservoir. That also leads to very low oil recovery and CO2 storage ratio. CO2 enhanced oil recovery is homogeneous and synergistic, but sometimes contradictory with carbon geological storage in the oil reservoirs. New advanced technologies are necessary to be developed to weaken the antagonism but improve the synergy. The storage-driven CO2 method provides a feasible way to paradigm shift in hydrocarbon recovery from massive emissions process to a net zero emission one. It significantly reduces the CO2 emissions but increases the economic benefit of the CO2 3. The storage-driven CO2 In our work, the storage-driven CO2 is proposed. Its main target is to realize the net zero or even negative CO2 emissions by storing the maximum CO2 in the oil reservoirs while accomplishing the maximum oil recovery. Here, a new advanced materials such as the DME is employed as an efficient agent for assisting the conventional CO2 oil recovery while enhancing the CO2 sequestration in the reservoirs. We can see that the DME significantly facilitates the CO2 solubility in the crude oil, especially at high pressure conditions. The improved CO2 solubility enables more CO2 to be trapped in CO2 oil. It is essential for CO2 storage in the oil reservoirs. This figure presents the mole fraction of the light components C1 to C5 and the gas phase for CO2, DME, and the crude oil mixtures. As for the CO2 DME crude oil mixture, the mole fraction of the light hydrocarbons in the gas phase is smaller than that for the CO2 crude oil mixture when DME is introduced. The extraction effect on the light hydrocarbon is highly inhibited, especially at high temperature conditions. The superiority of DME in improving the CO2 solubility enables it to have the potential for oil recovery while assisting the CO2 storage in the oil reservoirs. This figure shows the oil recovery in terms of the production time for conventional CO2-EUR and the storage-driven CO2-EUR. After introducing the DME, the initial oil recovery is increased. At the late oil production period, the oil recovery increases continuously, that is higher than that of the conventional CO2-EUR. That is to say, the storage-driven CO2-EUR favors the sustainable oil recovery. This figure presents the digital images of oil situation in reservoirs for conventional CO2-EUR and the storage-driven CO2-EUR. Conventional CO2 flooding exhibits the less sweep efficiency in the oil reservoirs, leading to a large proportion of the in-situ oil being untouched, while the storage-driven CO2-EUR is more superior in expanding the sweeping efficiency and enhancing oil recovery. This figure presents the CO2 storage ratio accompanied with the oil production time for conventional CO2-EUR and storage-driven CO2-EUR. We can say at the late oil production period, the CO2 becomes increasingly saturated in the residue oil and rock spaces. That results in the decreased CO2 storage efficiency. For the boost injection scenario, the CO2 storage ratio decreases with the gas injection rate. Gas figuring readily occurs and a large proportion of the injected CO2 flows through the dominating channels, while the gas injection rate is high. That leads to the decreased CO2 storage efficiency in the reservoirs. The DME can be used as a favorable agent for improving the CO2 storage in the oil reservoirs. This figure presents the net CO2 emitted from the incremental production and net CO2 emissions as a function of the cumulative oil production over the lifetime of an oil field. During the primary and secondary production, the CO2 emissions increases linearly with the increasing oil production. When conventional CO2-EUR begins, proportion of the injected CO2 is stored in the reservoir that offset part of the incremental CO2 emissions from the oil burning. And for the storage-driven CO2-EUR, the sequestrated CO2 exceeds the oil emission from the oil burning. That is to say, the sequestrated CO2 not only offsets the current but past CO2 emissions. That results in the linearly decreasing net CO2 emission. In addition, if we change to another flooding scenario, for example, the water alternating storage-driven CO2-EUR, we can find that it can store more CO2 in reservoirs. 4. The technical outlook. In the future work, we should develop EUR sequestration collaborative theory and technology to improve the storage-driven CO2-EUR method. First, more advanced functional materials should be synthesized to collaborate the oil recovery and the CO2 sequestration. Secondly, new materials should be developed to control the gas channeling in oil reservoir that can cause poor oil recovery and CO2 storage efficiency. 5. Conclusions. First, the conclusion. The DME can significantly facilitate the CO2 solubility in the crude oil. The DME can be used as a favorable target agent to improve CO2 storage in the oil reservoirs. The storage-driven CO2 UR is a promising way for the win-to-win target of oil production and CO2 sequestration. Finally, more advanced functional materials should be synthesized to collaborate oil recovery and CO2 sequestration. That is all of my presentation. Thanks for your attention. Thank you very much.